In the last episode, we've implemented the concept of levels and layers to add capabilities for complex fireworks. In this video, I'll be adding few helper functions and randomness. I'm planning for one more video after this one, so we'll be finishing off the overall algorithm today. So, we'll start off by deleting the shell2.1 we added, and revert the changes for shell11 to simple shape by changing isShell to false and tail lifetime to 1 second. As mentioned previously, Star Blast depends on the shape defined by shell11. If we were to enter edit mode, delete all vertices, then replace with a monkey head, the blast shape now becomes that of a monkey. Well, this shape with them tails looks more like a bird, but I hope you see the traces of Suzanne in there. Now, in order to build a general fireworks shell, there is a slight inconvenience. Not a huge issue, but inconvenience. Let's go back to edit mode and delete all points to see what I mean. So I think we can all agree that the most general blast shape of a firework is a sphere. However, Blender only offers two types of sphere primitives. UV sphere is not really a suitable option since point distance is not uniform. Icosphere has uniform point distance, but point count can only be controlled through a number of subdivs, which means we only have options of 12, 42, 162, 642, and so forth. This is pretty inconvenient when we want to make fireworks with a specific number of points. So first, I'm going to build a function that allows uniform point placement on sphere with specific numbers. I'm going to start off by adding a mesh plane. Doesn't matter which collection I add it in, but I'll add it to the top scene collection. Next, press a backslash on numpad to isolate. I'm going to combine these two window panes for more real estate. Unpin the node tree, then click on New to create a brand new geometry map. Call it Golden Sphere. I'll explain why it's called Golden Sphere in a minute, but let's start off by opening the side panel and by deleting input geometry. Instead, let's add a new integer and call it count. Add another input and keep it as float. Call it shell radius. Let's go to modifier panel and enter 10 for count and 1 for radius. Connect a point node from count, then connect to group output. Currently we should have 10 overlapping points on origin. They will later be placed on sphere surface. Now, the node tree we'll be making will be completely mass-based. I cannot fully explain the derivation, so please just trace what I do. Let's start with group input. Subtract 1 from count. Then add index node and divide it by the subtraction result. Use multiply and double it. Then, subtract 1 from the result. Use Ctrl J to frame, F2 to rename to Y. Next, use multiply to square it. Then, connect to subtract. Switch the connection from top to bottom socket, and subtract multiply result from 1. Then take a square root of that result. Use Ctrl J to frame, F2 to rename it to radius. Add mass node and change method to square root. Take a square root of 5 subtract 1, then multiply by pi. Frame them and name it phi. The reason for this name, golden sphere, is due to the use of this phi, which is the golden angle. Next, multiply phi by index. Frame, then call it theta. Connect cosine to the theta, then multiply with result of radius. Frame them and call it x. Duplicate everything in x with connections using Ctrl-Shift-D. Bring it down, change the method to sine, and rename the frame to z. From the result of x, pull out a combined xyz and connect to x. Then, connect the y we made in the beginning to y, and z frame result to z. Plug this result into position socket for points. If we go back to 3D viewport, we can see that points are randomly placed in space now. We will review the node tree in just a minute, so even if yours don't look like this, I'd advise you to keep going. If we increase count to 500, you can see the uniform placement pattern. It looks kinda unsettling, so let's put it back to 100. Now, place a transform geometry after points. Then, connect the shell radius to scale. We can now change the size of the sphere externally. Lastly, add a points to mesh to convert them to vertices. The shell builder geometry node only accepts mesh objects as inputs, so we want this output to be in verts. Alright, let's take some time to make sure connections and values are correct. In the past, I've made connection errors on the subtract and value mistakes on the square root, so especially watch out for these. Once we are done with this node tree, assign a fake user to keep it active. Then delete this plain object by pressing X. Select the shell11 object from outliner and add a new geometry node modifier. Select golden sphere from the dropdown and enter 501 for its parameters. If you run the animation, you'll end up with fireworks with 500 stars with uniform separation. By increasing animation length in shell lifetime, it looks much prettier with falling stars. For the next change, we can observe here that all the stars die at the exact same time. Such perfect work with perfect timing, and feels so artificial. So, add some variation and make it more real life. So the randomness factor I'm implementing is for shell lifetime and tail lifetime. But you can add more randomness control for other attributes as you wish. Also, instead of just adding random value node, I'm going to be making a randomness helper function for easier external control. First, add a random value node. Then, select only that node and group it with Ctrl G. Bring out the side panel, then delete all inputs except for seed. Then, add a float argument and call it base value. Add another float argument, call it randomness. For this one, clamp its input to between 0 and 1. Lastly, add an argument of type integer, name it multiplier. In the node tree, multiply seed with multiplier to disperse its results. When using same seed for multiple random values, result can become biased. Next, pull out a subtract from min and subtract randomness from 1 to reverse its effect. Then, multiply the result of random value with base value. Helper function is now complete, so call it Random Helper. So, let's configure the helper and use it for shell lifetime. First, pull out a group input from seed and leave the argument name as it is. Then, connect the shell lifetime to base value, which becomes a reference value. Pull out another group input from randomness and rename it to shell lifetime randomness. Then, connect the result of this helper to shell lifetime store named attribute. The way this works, say for example for randomness of 0, min input of random value node becomes 1, which is equal to max, so the reference value itself is outputted. Just as before, all stars die at the same timing. In case of randomness of 1, random value min takes a value of 0, making the result shell lifetime value be between 0 to 3 seconds. As you can see, their kill timing varies a lot. Lastly, let's try 0.2. In this case, min socket takes a value of 1 minus 0.2 times 3, which is 2.4. Thus, value will be selected from the range of 2.4 to 3 seconds. There is just subtle level of variety in this case. Since top seed value is set to 0 currently, there won't be any difference, but I'll set the multiplier to 10. Alright, we'll do the same for tail lifetime as well. Disconnect this group input and duplicate the random helper along with seed input node like so. For the base value, connect tail lifetime. Then, connect a new group input, tail lifetime randomness, to randomness. Plug the result into store named attribute. Set the parameter to 0.5 for decent level of variance. As some may have noticed, there's something weird going on here. There's a misplaced ray of light here, so let's segue into fixing this. To put it bluntly, this is a bug. I knew this was happening, but left off fixing it till now. This behavior is related to the combustion calculation we did in episode 3. So let's take a look at this calc mass node group. So currently the terminal mass setting for bursting star is set to 0 kg. When we calculate drag deceleration, we are using mass as denominator, so it is causing division by 0 issue. So instead of dropping mass to 0 kg, let's let it drop to 1% of its original mass. Add a multiply node and connect with mass in it, set the value to 0.01. Then connect to false socket of this switch. If we check the animation around the same frame, which was around 190, we no longer see that shooting ray of light. There still might be a chance of division by 0, but it is less likely to happen now. For the last change, I want to make the tail noise strength controllable. Currently, the tail noise is calculated here in calc tail noise, but the strength value is fixed to 10. So let's move this to shell builder as a design attribute. Let's select one of the shell object to change the displayed map to shell builder, then add a store named attribute. Keep the type as float and call it tail noise gain. Pull out a group input and call it tail noise gain. Now, select the launcher object and go to Fireworks node map. Go back to calc tail noise and connect a named attribute of tail noise gain. With current strength setting of 0 for both level 0 and level 1, the tail looks straight and sharp like porcupine spines. With gain setting of 20, it looks more like tentacles. A little bit disturbing. Okay, that's it for this episode. Let's review what we made. First, we've added helper function called golden sphere to shell 1.1. It is useful in case you want to place specific number of points uniformly on a sphere. Next, a helper function to control the randomness externally. If you choose to avoid reusing same seed value, use different values of multiplier for each randomness helper. For calc mass, we added a minimum mass to avoid division by 0. Lastly, for calc tail noise, we added an external control for tail noise strengths. Alright, we are done with logic building portion using geometry nodes. Thank you for sticking with me through this long series. I will be reorganizing argument list and provide example of shells to finish off the series in next episode. Thank you for watching and see you next time.